Good afternoon, everyone. I'm Chaoyuan Zhou, and I will present Optimizing Object Detection via Matrix-Driven Training Data Selection. And this work will start along with Yuming Guo, Qingxue Lü, and Ji Yuan. We are all from OneWorld Space Tech Service Corporation Limited. My discussion will mainly cover this four parts. First, we will start by discussing the challenges and motivations behind our research. And then we will introduce our methodologies for optimizing dataset selection. In the third part, we will show experiments that we conducted to validate our approaches, discuss the setup, the data we used, and the outcomes of this experiment. And finally, we will summarize our contributions and propose directions for future research in this area. Let's begin with the background of the competitions and challenges in object detection. Object detection, a critical task in computer vision, faces significant challenges when training models, especially in environments where data is limited and often lacks labels, posing difficulties in applications of vision algorithms. Traditionally, the focus has been on contrasting robust models through intensive training strategies and tunings of hyperparameters on large-scale well-annotated datasets like COCO and VOC. In contrast, these computations involve finding limited annotated images to train a robust model, which can be adapted to unknown and unlabeled target set. In training phase, model configurations and hyperparameters are not allowed to tune, and the aim is to enhance object detection performance under these challenging conditions. Mathematically speaking, this process can be expressed as the formula. We are seeking to optimize performance of a model M based on the relationship between the S and T, namely source pool and target set, respectively. And there are two constraints. The first one, the source pool is limited to a group of datasets with various characteristics. The second one is about the budget of the selections of images. And in this computation, images utilized to train such a model are limited to up to only 8,000. Therefore, the call to tackle this problem is to find the similarity or distance as a metric for finding the most informative data. Distance-based approach, phase inception distance, or FID as in this instance, which was utilized by the baseline model, evaluate the distance between the features or distribution between images. In this formula, μS and μT are derived from the inception retrieval network, and TR denotes the chase operation, and sigma S and sigma of R are the corresponding covariance matrices. In the meantime, average precision is the most popular evaluation matrix in object detection task, which can be calculated by the second formula, in which the P interpolated of R denotes the interpolated precision at record level R, and capital R denotes the set of record values ranging from 0 to 1 with an increment of 0.1. So different from previous work in which AP is calculated using the whole data set, it qualifies the accuracies of the models in terms of being able to detect objects collectively across various threshold levels. In this work, we propose to utilize image-wise AP as the matrix to select 8,000 images from the source pool. This is the flowchart of our proposed method. As we can see, the test set, including the chain and test data set, are provided by this computation, region 100. It consists of images from 100 cameras around the world, posing challenges to the participant. To begin with, the angle of views, brightness, and images qualities varies from different cameras. Secondly, the dataset features densely vehicles, complicating accurate localization, especially for the remote objects. And last, the manual erasing manipulations on test images can lead to discrepancies between the training and testing data. And the source pools consist of 7 popular datasets in object detection, which includes a variety of popular datasets such as ADE, BDD, Cityscape, COCO, and etc. So, in the initial step, we have a data exploration to better understand the dataset. To tackle the initial lack of labeled data, we conducted pseudo-labeling using a YOLO-VAX model. We use these models to generate pseudo labels as the guidance and train a retinal net model. And then we use this model to predict on images from the source pool and rank these images with the image-wise average position. Therefore, we select the top 8,000 images from the source pool as the training set and apply the mosaic augmentation to the selected images. This technique enhances the diversities of training scenarios by combining different images segments into the single composite images, improving the model's ability to generalize across various image input. It is followed by utilizing this augmenting data to train a retinal model with the preset configuration and hyperparameters required by this computation. And last, we use this model to predict images from the target set, namely the test A and B part of this computation. To better understand different data sets from the source pool, we conduct statistical analysis based on the localization and size of bounding boxes of each data set. Each point on the scatter plot represents the position of an object within an image frame, providing insight into how objects are typically distributed across the image space. For the position scatter, the horizontal and vertical axes are normalized center coordinate of bounding boxes. Similarly, for the side scatter, it demonstrates the normalized size of bounding boxes for each data set. Based on this analysis, we can see that COCO dataset exhibit a well-balanced distribution, and this is a key reason why we narrow the range and select COCO as our primary source for training data. In the meantime, to have a quantitative comparison of the efficiencies of different datasets, we randomly select 1,990 images from each dataset and implement training respectively. Performance shows that the model trained on COCO outperformed the others. This outcome supports our choice of COCO for training due to its diverse and balanced representation. We also exploit the quantitative impact of various training methods. Table 3 shows evaluations on test A, which indicates that the mosaic augmentation enhanced performance across most metrics for the random and SMP cases. Table 4 demonstrates that our best model, AP with COCO and mosaic, achieved 0.228 AP score, outperforming others in considerations of AP. The post-augmentation heat map on the right reviews mosaic augmentation significantly expand the diversity of object positions. In terms of quality comparison, this figure shows the prediction result of the baseline model and our BAF model, in which the green bounding boxes are ground truths, while the red ones are the predictions. We can observe that our BAF model achieves better recall. Therefore, in conclusion, we introduce a methods that utilize the image-wise AP for selecting the most relevant training data, and experiment results demonstrate its advantage. Secondly, we implement an analysis on the bounding box distributions to guide the selections of the data sources. And last, we employ the mosaic augmentation on the images to increase the training data's variance, efficiently broadening the model exposure to diverse scenarios and enhancing its generalization capacities. Our code has been available at this link, and our future work will focus on exploiting multiple datasets and a hybrid of raw and augmented images. That is all. Thank you very much for your attention.